Welcome to Math Science History. I'm Gabrielle Birchak, your host. I have a background in math, science, and journalism, and today, it's Thursday. I'm just going to do a quick episode in honor of Women's History Month, and I wanted to feature one woman whose work still quietly runs the world, or should I say, the universe. Today's One Brilliant Thing was a way to take the universe, which is a chaotic glitter hurricane, and file it into something that you could actually study. So who was this brilliant woman? Her name was Annie Jump Cannon. What a great name. If you have ever heard the sequence OBAFGKM, you have met her legacy. Astronomers still use that spectral classification system to describe the stars. It is basically a cosmic organizing spell, and it works. That sequence is part of the Harvard Spectral Classification System, which Cannon helped refine into the streamlined form widely used today. Now, that string of letters looks like nonsense at first, but people invented silly mnemonics to remember it. The classic one went, "Oh, be a fine girl, kiss me." But honestly, I find that a bit offensive. And it was very early 1900s, very cringe, very memorable. But I'm going to go with a bit more of a feminist vibe. And I'm going to go with obviously bold. A feminist generation keeps marching. OBAFGKM. For me, I translate OBAFGKM into a sensory map. Letters become temperatures, and temperatures become a color ladder. The letters are just names, but the ladder gives them meaning. So think of OBAFGKM as turning a single temperature dial. You turn it all the way up, and the O stars announce themselves with helium. You take it down a step to B, and helium is still strong, but hydrogen starts to show its hand. At A, hydrogen takes center stage. When it cools down into F and G, hydrogen softens while metals become clearer in the spectrum. And by the time you get to K, those metal signatures are bold. And at M, the air is cool enough for molecules. So titanium oxide paints the spectrum with wide, dark bands. So the stars in our night sky have colors, and they correlate to that acronym, OBAFGKM. O is Oxford blue. These are the hottest stars in our night sky, and they are between 30,000 and 50,000 Kelvin. They are rare. That dark blue shows that the star is composed of ionized and neutral helium. Moving on to B, bluish white. These stars are also very hot, but not as hot as the dark blue ones. They're between 10,000 and 30,000 Kelvin. And that color shows that they are also neutral helium, but they're also strongly composed of hydrogen. Moving on to A, alabaster white. Those white stars that you see in the sky, they are between 7,500 and 10,000 Kelvin, still very, very hot and composed strongly of hydrogen and ionized metals. For the letter F, F represents the color fawn or flax, which is a yellowish white. These stars are between 6,000 and 7,500 Kelvin, which shows that they have weaker hydrogen and more ionized metals. For the letter G, gold, yellowish. These stars are composed of weaker amounts of hydrogen and are ionized and have neutral metals. They are between 5,200 and 6,000 Kelvin. So, for example, our sun is listed in this classification as G2. Moving on to K. These stars that you see in the K classification are orange or kumquat. K for kumquat. These stars that you see have weaker hydrogen and neutral metals. They are approximately 3,700 to 5,200 Kelvin. Finally, the classification M, reddish maroon. These stars have little or no hydrogen at all. They are neutral metals and have molecular bands like titanium oxide. And these stars are about 2,400 to 3,700 Kelvin. But the real point here is not the rhyme. The real point is that Annie Jump Cannon helped turn starlight into data, and here is the setup. At the end of the 1800s and the start of the 1900s, astronomy got a new superpower. It was spectroscopy. By the late 1800s, Astronomers were using spectroscopy, spreading starlight into a spectrum and recording it on photographic plates so the patterns could be compared and cataloged. Instead of only looking at where a star was, astronomers could spread a star's light into a spectrum, like a rainbow barcode. Those dark and bright lines in the spectrum told you what the star was made of and, crucially, what its physical conditions were. At Harvard College Observatory, thousands of photographic glass plates captured those spectra. Each plate held a crowd of stars, each star leaving behind its own thin streak of light. Someone had to look at those plates, identify those patterns, and classify the stars consistently. Well, that someone was not a single person. At Harvard College Observatory, a large effort grew around analyzing those plates, and a group of women became known as the Harvard Computers for their work processing and cataloging astronomical data. Cannon was one of those astronomers, and she became especially known for her speed and consistency in classifying stellar spectra. And Annie Jump Cannon became the one who took stellar classification and made it fast, consistent, and usable at a massive scale. Cannon did not begin with a blank slate. Harvard already had earlier classification schemes. They were complicated, they used lots of letter categories, and they reflected an era when astronomers were still figuring out what the spectrum lines meant. Cannon's genius was partly scientific and partly practical. She simplified, she standardized, she kept what worked and threw the rest into the recycling bin of history. Early spectral categories used letters that were not originally arranged by temperature, and Cannon's major contribution was to simplify and reorder the system into the sequence OBAFGKM, which is strongly associated with the star's surface temperature in modern astronomy, as I just went over. So she ultimately emphasized the sequence, which corresponded to temperature sequence from the hottest stars to the cooler ones. It was not alphabetical, it was physical. In other words, Cannon helped shift classification from these spectra look kind of similar to these stars were actually different kinds of objects. Then she did the part that makes my brain short circuit in admiration. She classified the stars, a lot of stars. Then she helped produce one of the biggest data products in early astrophysics. Working from those photographic plates, Cannon and her colleagues produced the Henry Draper Catalog, which published spectroscopic classifications for 225,300 stars in the main catalog volumes released between 1918 and 1924. It was 9 volumes published in the Annals of Harvard College Observatory. After Edward C. Pickering's death in 1919, Cannon oversaw completion of the remaining volumes and continued extensive classification work in the Henry Draper extension publications. Depending on which count you use, her lifetime total was often summarized as hundreds of thousands of stars, frequently cited around 350,000. That's a lot. So let's translate that into human terms. That was not, she wrote a paper. That was, she performed a census of the sky. That is why she was called the census taker of the sky. And the most delightful part was how direct the work was. It wasn't abstract. It was not metaphor. It was literally someone sitting with glass plates, examining spectral lines and making careful judgments over and over for years. To some, classification can sound boring. For me, it sounds like heaven. A shared classification system lets astronomers compare huge numbers of stars consistently, which helped astronomy scale into astrophysics. There is a modern instinct to imagine this as mindless mechanical labor, but it truly was not. Classification is where science stops being a scrapbook and becomes a machine. A classification system decides what questions you can ask next. It tells you what counts as the same, what counts as different, and what counts as weird enough to deserve a closer look. Once a star had a spectral type, astronomers could connect it to other properties. Over time, spectral classification became a key piece of how scientists understood stellar temperatures, stellar evolution, and the structure of our gorgeous, beautiful, wonderful galaxy. So yeah, the letters looked like a weird alphabet soup, but they became a shared language. They let astronomers talk to each other with precision. Canon's system also did something else that was sneaky and powerful. It made astronomy scalable. If you could classify stars consistently, you could compare thousands of them, the tens of thousands, then hundreds of thousands. You could start to ask statistical questions. You could look for patterns across populations of stars instead of treating every star like a one-off curiosity. That is the bridge from beautiful objects in the sky to astrophysics. And Canon quietly built that bridge. There's also a human side to this story that matters for Women's History Month. Canon worked in an era when women's scientific labor was often treated as support work, even when it was foundational. The Harvard computers produced core results that underpinned the field, and it took a long time for the world to fully credit what they had done. And Canon did receive major recognition during her lifetime, including major honors in astronomy and the creation of an award in her name that supports women in the field. But the deeper recognition is simpler. Her work endured. Her system stayed. Her classifications remained useful and still remain useful. When a scientific idea survives, it is usually because it is doing real work. So, for this week, while the universe continues doing its chaotic glitter hurricane thing, I want to pause and salute the woman who looked at starlight and said, I can organize that. I love that. So, what are our 3 takeaways? First, classification is not boring. Classification is power. It shapes what science can become. Second, Annie Jump Cannon helped turn the night sky into a data set, one spectrum at a time. Third, the next time you hear OBAFGKM, you could remember this. That sequence was not just a mnemonic device. It was a woman's method made permanent. And with that being said, I'm going to go back to my more feminist vibe. Obviously bold, a feminist generation keeps marching. Thank you for listening to Math, Science, History. And until next time, which is actually tomorrow, Flashcard Fridays, Carpe diem, my friends. Thank you for listening to Math, Science, History. If you want the next episode as soon as it drops, just tap follow in your podcast app. Math, Science, History is brought to you by caffeine. Delicious, delightful, life-supporting caffeine. If you'd like to support the show, you can find the coffee cup link in our show notes or at mathsciencehistory.com. Just click on that coffee cup. Your donations don't really go to coffee, but they really do help cover production costs. The MSH theme is public domain from the late, great music composer and professor, Dr. Lloyd Rogers. All other music is public domain from Pixabay. Until next time, Carpe diem.